Hello everyone, thanks for attending today's seminar and also thanks for the work of Sean. And I'm very glad to introduce today's speaker, Professor Rita Meyer. So Renate is a professor in the Department of Statistics at the University of Auckland. And I guess she's, worked in the university since 1994. Bayesian inference and also MCMS methods, and in particular, the focus on the application with time series analysis with application with astrophysics, and in fact, one very important thing that Renate was my PhD supervisor, and we worked together for like 4 years. And so I'm very happy and thrilled that she can come here today and give a talk today to talk about her recent work on Bayesian spectral analysis of multivariate time series. So I think now I can pass the time to Renate to give her talk. Thanks, Ira.
Thank you very much, Ajahn, and thank you all for coming and sorting out the technical problems. I hope everybody can hear me. So it's a really great pleasure to be here in Cambridge and to see Ajahn again, and my first time at Cambridge University. So I'm really grateful for the invitation. Thank you very much for having me. I'd like to talk about some joint research on Bayesian nonparametric approaches to analyzing multivariate time series. That's sort of a line of research that goes back quite a few years when Claudia Kirch from the University of Magdeburg in Germany visited Aukland University. And so she is a sort of an expert on bootstrapping time series and change point analysis. Quite theoretical, whereas I would call myself more of an applied Bayesian statistician. So we're wondering what type of research project we could work on. And what we had in common was we used, in one way or another, used the Whittle-likelihood. And so that's how all this originated. And today I want to talk about analyzing multivariate time series. And this has been a large part of Ajahn's PhD thesis as well. And joint work also with Kate Lee, who was co-supervisor. So as Ajahn has already mentioned, one of my current focus has been actually for quite a long time. My focus is on analyzing gravitational wave data in collaboration with astrophysicists. But I'm not going to talk about gravitational waves today. In the biostats department, I thought that was not really of much interest. So one of the examples I want to start with is analyzing the electrical activity of the brain in an EEG, and I think that's one of applications that occurs quite a bit in medical statistics. So the motivating example is a bivariate EEG time series. It's a voltage measurements over a 5-second period, sampled at 200 Hertz. At the right and the left frontal cortex of an adult male rat. It's called the rat A. And if you just look at the individual time series, at each time series you see sort of serial correlation. They're certainly not independent. You've got interactions between the time series over time, and you see stochastic behavior. You see cycles which different heights of the peaks and different lengths of the period. So if we want to analyze this statistically, one of the most often made assumptions is that of stationarity. Do not assume that observations are independent. And that's usually no problem for any point estimate, but this dependent structure is crucial if you want to quantify the uncertainty. That uncertainty quantification depends a lot on the dependent structure. So the question I want to answer is, how do we quantify this uncertainty without making any too restrictive parametric assumptions? Please feel free, if anything is unclear, interrupt and ask questions. So to set some notation, let's say ZT is a d-dimensional mean-centered stationary time series and absolutely summable autocovariance function. The autocovariance function is a positive definite matrix valued function, and what I've plotted here is this empirical autocovariance function of time series, bivariate time series, and we see that decreases. The autocorrelations decrease, or the autocovariances decrease over time. The autocovariance function uniquely characterizes the dependent structure, but so does the spectral density, which is the Fourier transform of the autocovariance function. So for a d-dimensional time series, that spectral density is a complex matrix value function, periodic, and for each frequency, each of the frequency omega in the interval 0 pi, it is a Hermitian positive definite matrix valued function. So here's, for instance, the spectral density of a bivariate vector-autoregressive moving average time series, and on the diagonal we've put the spectral density of each of the two time series. First one, sort of the spectrum of a moving average model. Second one is the sharp peak of an autoregressive model of order 2. So the diagonals are real. The off diagonals are complex valued. They've got a real and an imaginary part for spectrum, which gives us sort of the interaction between the two time series. So if we want to estimate that spectral density non-parametrically, we usually use the periodogram matrix, which gives us the on the diagonal the usual periodograms of each time series, which is just the squared modulus of the discrete Fourier transform, and of the off diagonal are the mixed products, and they are complex valued. This is, for instance, the corresponding periodogram from a realization of size 4096 of that Varma model. So I've just simulated from the Varma model time series of length 4096 and calculated the periodogram, and we see it's just a wiggly version of the spectral density matrix. So the periodogram is asymptotically unbiased, but these wiggles, they don't decrease over time. So it's not consistent estimators. And that's why people in the frequentist literature, they use smoothing techniques to get consistent estimators of the spectral density matrix. And there's various methods that are being used, and the recent review is given by von Sachs. Now, if we want to use a Bayesian approach, and the Bayesian nonparametric approach, we need, first of all, a likelihood function, and we need a nonparametric prior on the space of Hermitian complex matrix valued functions. Let's start with the likelihood. And what we're going to use is the Whittle likelihood. It's a likelihood approximation that, for instance, if you assume Gaussian distribution, in order to evaluate the likelihood, you would have to invert a high dimensional matrix, which is computationally quite expensive. And therefore, way back in the 1950s, the New Zealander Peter Whittle had already come up with an approximation of a so-called multivariate Whittle likelihood, and that is based on the properties, the asymptotic properties of the periodogram matrices. They are asymptotically independent, which is important, and they have a complex Wishart distribution, independent complex Wishart distribution for each Fourier frequency. So we're using the asymptotic independence and this asymptotic Wishart distribution, and we can write down a likelihood approximation. It's an approximation, it's exact only for Gaussian white noise, but it gives A good approximation originally was meant for approximating Gaussian time series, gives good approximation also for non-Gaussian time series. And that's the form of the multivariate Whittle-likelihood. It's used very often. So that's one likelihood we could use, the Whittle-likelihood. And next component is a prior. We need a prior on that non-parametric prior on that space of Hermitian positive definite matrices, spectral density matrices. What people have used is the Cholesky decomposition. In the Bayesian non-parametric literature, what people have done is they smoothed each component of the Cholesky decomposition in order to guarantee that the estimate is again Hermitian positive definite. And they've used smoothing splines or smoothing splines to smooth each of those components. If you keep the number of splines variable, then you need to use some sort of reversible jump type techniques if you jump over dimensions. And that's usually quite difficult to tune and difficult to diagnose convergence of. Alternative approach was given recently by Hu and Prado. They used a variational Bayes approach, so they used variational inference. They fixed the number of smoothing splines and then used the variational inference approximation. And that's computationally a lot faster as well as reversible jump MCMC. Here, I want to suggest an alternative, and that is the Bernstein HPD matrix gamma process prior that we developed in 2020 with another PhD student, Alexander Meier. HPD stands for Hermitian positive definite, using that abbreviation quite a bit now. And it does not use the Cholesky decomposition. What it does is it basically generalizes the Bernstein-Dirichlet process prior to the multivariate case. So for univariate time series, in 2003, Chowdhury et al., they used the Bernstein-Dirichlet process prior. And that is a prior that basically uses the Meier approximation to any continuous functional spectral density is a continuous function on the interval 0 pi. So you can restrict it to the interval 0, 1. And what they did is they didn't use smoothing splines, they used Bernstein polynomials to approximate that univariate spectral density. And they, the Bernstein polynomials, if you normalize them, they are just beta densities. So you can look at it as a mixture of beta densities. So the number of mixture components, this little k, the summing over j from 1 to k, it is a smoothing parameter. The smaller k, the smoother the representation. So by putting a prior on k, we get an automatic data-driven estimate of the degree of smoothing. But if you leave k variable, then again, if you've got a weighted average of beta densities or Bernstein polynomials, if you put a Dirichlet prior, for instance, on the weight vector, the weight vector changes in dimensions and you would have to use reversible jump if you jump over dimensions. So Chowdhury instead let the weights be induced by a distribution function phi on the interval 0, 1. So phi of j minus 1k over j over k is the distribution of the value of the distribution function of phi over that interval, j minus 1 over k to j over k over the subinterval. And then we put a gamma process, or a Dirichlet process prior on phi, so non-parametric prior on the distribution on the interval 0, 1. Dirichlet process is just a normalized gamma process, so you can look at it as a infinite gamma mixture of beta densities. And the increments of that gamma process, they have independent, or the increments are independent gamma distributed. So if we want to generalize this to the multivariate case, instead of a univariate time series, we've got a d-dimensional time series. But we use the very same construction, but now the weights are matrix valued positive definite Hermitian weights. So the problem becomes, how do we define a matrix valued gamma process which has independent matrix gamma distributed increments? The usual generalizations for that, similar to the construction of a gamma process using the Kingman construction, we want to use the Kingman construction here to construct such a matrix valued gamma process. Problem with the usual generalizations of the gamma distributions, like the Wishart, is that they are not infinitely divisible. In Kingman's construction, we need infinite divisibility. But we first can construct an infinitely divisible matrix gamma process, a matrix gamma distribution, sorry. And we basically generalize the HPD gamma distribution that was introduced by Stelzer et al. In 2014 from the real to the complex case. And that matrix gamma distribution that's defined using the Lévy-Kenshin representation of its Laplace transform, with this gamma Lévy measure given here. That's basically use that infinitely divisible HPD matrix gamma distribution, and then we'll use the Kingman construction by using the Lévy measure as the mean measure of a Poisson process on the interval 0, 1 and the positive definite matrices. Looks like that, looks very theoretical. But then we have a Hermitian matrix gamma process, and that's what we put on that matrix valued distribution function. Next problem was, how do we actually simulate from that process? And for that, we use an infinite series representation similar to the stick breaking representation of the Dirichlet process, which some of you might be familiar with. So that's for the actual posterior computation, for simulating from that process. That was all a little bit theoretical, but basically how it works is that any realization of that HPD matrix gamma process is a discrete distribution. So if we sum up those realizations that fall within a certain subinterval, and I've color-coded them, we sum those up, they will give the weights that are associated with the corresponding Bernstein basis. And then by taking a weighted average, we get this smooth mixture representation. That's all that's behind the complex construction, the Kingman construction. So what we did here in this paper is we used that HPD matrix gamma process prior, but not with the Whittle likelihood, but we generalized the Whittle likelihood. And the idea is that parametric models are usually very efficient when they're correctly specified, but they can give biased results under model misspecification. So the idea is to use an auxiliary parametric model, but make it more robust by getting nonparametrically close to that parametric model. Or you could look at it as making a nonparametric approach more efficient by using an auxiliary parametric model. And similar ideas, they've been floating around in the literature before. Hjort and Gladden, way back in 1995, used that for nonparametric density estimation, and Kreis and Papavoditis used it for nonparametric bootstrap of univariate time series. So what is this generalized Whittle likelihood? It is actually a generalization of the ordinary Whittle likelihood. It has this form. The idea is we start with a parametric model for our time series, say a vector-autoregressive model of some order P. So a parametric auxiliary model. We Fourier transform the time series into the frequency domain, and in the frequency domain, we correct for potential model misspecification. multiplying by a correction matrix. And that correction matrix contains the, more or less on the diagonal, the ratio of the parametric auxiliary model to that of a nonparametrically modeled spectral density. That's just a non-parametric correction of the parametric model, and then we back transform into the time domain. This is just a linear transformation, Fourier transform multiplying by a diagonal matrix and inverse Fourier transform. So the whole transformation is just a linear transformation, and the density induced by that linear transformation under that parametric auxiliary model and under that vector-autoregressive model, that's what we call the generalized Whittle likelihood, and that has this form just using the change of variable technique. It is a generalization. If you would start with a vector-autoregressive model of order 0, so just Gaussian white noise, the spectral density would be constant, you use this construction, this transformation, frequency domain, correction, back transform into the time domain, under the Gaussian white noise model, then you would get the Whittle likelihood. But you can imagine that you could start with a better model than Gaussian white noise for the dependent structure of your time series. So that's the idea behind using a better parametric start. We could show various properties that, well, this is a generalization. If the parametric model is the correctly specified, then the generalized Whittle likelihood is the parametric likelihood. But even under model misspecification, it's still asymptotically unbiased. And we can also show mutual contiguity of the Whittle likelihood and the generalized Whittle likelihood under the Gaussian distribution assumption. So what we did in practice is we used the generalized Whittle likelihood, which now depends on the parameters of the vector-autoregressive model, and it depends non-parametrically on the spectral density. And we use that Bernstein HPD matrix gamma process prior, but we put it not on the spectral density itself, but we put it on the correction function, because that correction matrix will be a much, if the parametric model already gives a reasonable approximation, that correction matrix will have much smoother, flatter components, because it's the ratio of the parametric and the non-parametric spectral density. And Bernstein polynomials are quite good at approximating flat functions, but not so good at approximating functions with sharp peaks. So the peaks have already been flattened out or pre-whitened by the parametric model. And there was usually a good trick, this reparametrization, putting the prior on the correction function. And then we're not treating the vector-autoregressive coefficients as fixed. We're estimating them simultaneously with the non-parametric spectral density. And we don't need to use reversible jump for that. We can just use an ordinary Metropolis-Hastings algorithm, usually adaptive. We've got implementation in a package. We've done sort of a big simulation study. I just want to show you two cases of how that method comes. And the two cases are one where we've simulated repeatedly from a vector-autoregressive model of order 2. So that's the correctly specified case. The vector-autoregressive model is correctly specified, and we're using a vector-autoregressive model as our auxiliary model. And one where we repeatedly simulate from a moving average model, so it's a misspecified case. If we just look at what happens for increasing sample size from 256, 512 to 2024, we see that the mean squared error for the generalized Whittle likelihood, for the others as well, it decreases with increasing sample size. So that's sort of empirical evidence for posterior consistency, the posterior distribution contracts with increasing sample size around the true spectral density. If we want to compare the parametric approach, if we fit a vector-autoregressive model to our realizations, which are generated from a vector-autoregressive model, we would usually assume that that outperforms any non-parametric method and also the semi-parametric method where we use the generalized Whittle likelihood. And that's the case. It is much better than the parametric model based on the Whittle likelihood. But here, the generalized Whittle likelihood can take advantage of the correctly specified auxiliary parametric model, and it gets smaller mean squared error, and it has much better frequentist coverage than a method based on the ordinary Whittle likelihood. So it gains the efficiency of the parametric model, and in the misspecified case, there it basically gains the robustness of the non-parametric model. It has a smaller mean squared error and much higher coverage than the non-parametric as well as the parametric technique. So it's gains the efficiency of the parametric model and the robustness of the non-parametric model in the misspecified case. I want to show you a couple of examples of that performs in practice. And one of those examples that have been analyzed in the time series literature a lot is the Southern Oscillation Index. And the El Nino Southern Oscillation is an irregular periodic variation of the winds and the temperature, sea temperatures in the Pacific Ocean. And it affects a lot of countries. And we usually distinguish between a warming phase, the El Nino, and a cooling phase, the La Nina. And then in the Southern Oscillation is basically a standardized difference of the mean sea level pressure difference between Tahiti in the east and Darwin in the west. And it's sort of an indicator of this Southern Oscillation. On the other hand, we've got for the same months from 1950 to 1989, I think this time series goes. It's from the R package. So it's automatically included in R. We've also got a recruitment time series. That's the number of fish that spawned in those months. And fish spawn better in cooler waters, so we would expect a relationship between the Southern Oscillation and the spawning fish. If we use this non-parametric approach using the ordinary Whittle likelihood, we get spectral densities estimates that look like that. And you can see that those spectral density estimates, they haven't picked up that sharp peak that we see in the periodogram, that's just the annual variation, the annual peak. And that is basically because the Bernstein polynomials are not so good at picking up these sharp peaks. So then we said, oh, well, we'll use a parametric auxiliary model and we'll use a vector-autoregressive model, and we need to decide what order we're going to use. We just want a parametric model that gives a reasonable fit, but does not give a perfect fit. I mean, if you would increase the order up to infinity, you would get a perfect fit, but you will get an overfit. So we just want a reasonable fit, and what we use is a simple elbow criterion where we just calculate the maximum log likelihood, and where we see an elbow, we think it has dropped off significantly, but we're not overfitting. We're leaving some room for the non-parametric correction. So if we use that with the autoregressive model of order 5, we get we can now pick up that sharp peak with a generalized Whittle likelihood. And that's what's been found in the literature using other techniques as well. And we also have this low frequency, more wide peak, and that is usually interpreted as the El Nino effect. The El Nino usually occurs every 4, 5, 6, 7, 8 years, and it lasts for a few months and varies quite a lot in intensity. So with this generalized Whittle likelihood, we get we can pick up these peaks. And if we look at the squared coherence as a linear measure between the two time series, we see also the sharp annual peak and the low frequency peak, which could be the El Niño effects. Fish spawn much better in the waters. I've already mentioned one paper that appeared last year from Hu and Prado. They used a variational inference approach, and what they analyzed was wind speed at 6 different locations in California. 3 of those locations were around Monterey on the coast, and 3 were further inland around Sacramento. And these are, I think they were averaged, or they were medians over, over 2 hourly periods, I think. Or we took the median wind speed measurement over 2 hourly periods and then recorded those for 6 months. And that's these 6 time series that we see here. And I think they have first order difference as well. Again, if we use an elbow criterion, we would probably choose a vector-autoregressive model of order 10. We use that as our theory parametric model in the generalized Whittle likelihood. We pick up in these individual spectral densities of these 6 time series. They have these sharp daily peaks, as well as sort of half daily, quarter daily, hourly peaks of harmonics. Hu and Prado, they used a variational inference approach, so approximation again, and they also used the Whittle likelihood. And what they found was quite striking. If they calculated the squared coherences, they only found non-zero squared coherences for pairs of wind speed measurements in the same region, so on the coast or inland, but not in between. Sort of the mixed pairs that are sort of wind speed measurements on the coast, and one location on the coast, one location inland, they were all 0. No correlation whatsoever. So we reanalyzed those data, got similar squared coherences for the pairs within a region, but for pairs between regions, we also got non-zero squared coherences, where we have sharp daily peaks, quite high, but then the sort of the half daily, quarterly, hourly peaks, they were quite small. I think that sort of makes sense, even if those wind speed measurements are about 200 miles apart, the daily patterns will be similar wind speeds, but sort of hourly or minutely patterns will be quite different. And we also used the variational inference approach by Hu and Prado, and we found that variational inference is very sensitive to the choice of the learning rate. If we choose a smaller learning rate, we get similar non-zero squared coherences, so that basically corroborates the results with a generalized method. So I think that was just an artifact of a learning rate, but that was chosen too small, too large. And last not least, I want to get back to that EEG example. We had the EEG measurements on red A, but we also got EEG measurements on red B. And for red B, we see a striking occurrence of spikes. And spikes are usually sort of a landmark for epileptic activity, but not just the occurrence of spikes, but the synchronization of the spikes. Spikes usually occur when there's some synchronization of the neurons at the electrode at which they are measured. If you have synchronization of the spikes at different electrodes, then that usually indicates some it's a pathological synchronization that indicates some epileptic seizure. We probably already see by eye that there is some synchronization of the spikes at the right and the left hemisphere. If we use this generalized Whittle likelihood estimate and the Bernstein-Dirichlet matrix gamma process prior, calculate or estimate the spectral density matrix for each individual spectral density. The red curve is the spectral density of red A that didn't have the spikes. The blue one is red B, and we see peaks at about 8-9 Hertz. And then they sort of drop off at higher frequencies. Same at the right channel, similar at the left channel. If we look at the square coherences between the right and the left frontal cortex electrodes, we see for the red A only a peak at 9 Hertz, but then the square coherences drops off to a much lower level over all the higher frequencies, whereas for red B, the square coherences stay elevated at about 4.8, close to 1. So strong pathological synchronization for red B, which indicates epileptic seizure. So I'd like sort of to, or the main point I wanted to make is that we can, by taking an auxiliary parametric model, we can make a nonparametric approach a lot more efficient and accurate. But we do not lose any of the robustness in the specified case. We've got a proof of posterior consistency but only for when we combine the Bernstein-Dirichlet matrix gamma process problem with the ordinary, with the Whittle likelihood. For the generalized Whittle likelihood, the proof is a lot more technical, because there we can no longer use the independence between the parallelograms. That's what we use for proving posterior consistency in the ordinary case. So that's still outstanding with preliminary results, but not full proof of posterior consistency. But we've got R code and at least empirical evidence for posterior consistency and reasonable performance in the simulation, as well as examples that we looked at. So in the future, what we want to do is make the code more efficient and make it applicable to long time series, because my main focus is on analyzing gravitation, and these are usually sampled at either 4 kilohertz or 16 kilohertz. So we've got really long time series, and make this applicable to those long multivariate time series and analyze the dependent structure there. So that's the plan for the future. So thank you very much for your attention.
Any questions?
May I ask about stationarity?
Yeah.
So, for example, with financial data, the assumption of stationarity probably wouldn't be satisfied. So, how would you then adopt such a kind of approach to look at correlations between?
To look at the correlations, well, you could probably use a parametric approach where you maybe assume at least local stationarity, and there were various approaches that use the parametric sort of a time varying autoregressive, or where the coefficients of the autoregressive models are time varying. I think that would be the standard parametric approach. It's a very interesting problem for Bayesian nonparametrics, how to do this nonparametrically. I've got an answer for the univariate case. It's actually, I've got a couple of references. That's the last one here. The last one, where is it? No, I haven't got it. It's not on there. But we've got a preprint out on using a Bayesian nonparametric approach for locally stationary time series, where we can prove posterior consistency under the Gaussian distribution. No, I think it's actually the proof is general, not just for Gaussian time series, but for general. And that seems to work quite well if we compare it to usual frequentist approaches. But for multivariate time series, I think that's quite a tricky problem. And what an answer to that. That might be quite a nice research problem. Thank you.
Sorry, forget my ignorance because I haven't done time series in a I'm always curious of what are the advantages of using the frequent domain as compared to the time domain, which I thought it was always easier for identifying models and everything.
Well, the main reason for going into the frequency domain is that if you've got long time series of, I don't know, 500 or 1,000, you would have to invert a 1,000 dimensional covariance matrix to evaluate the likelihood. And if you use a Bayesian approach, you have to do this in every MC iteration. So that's really time consuming, and that's why people use approximations. One such approximation is the Whittle likelihood, but you could also use subsampling or some other approximations, or but even or you could use variational inference, but even variational inference uses the likelihood approximation. So it's basically computational. You want to have something that's fast.
I'm quite interested in this idea of like trading off between the parametric and non-parametric.
Yeah.
So you used the elbow initially to like get a cutoff for like how peaky you would allow it to be in the frequency domain, right? Mm-hmm. Do you have a way of like trading off? I want my correction to correct, some, but not a lot.
Yeah.
Do you have any parameters inside here that is kind of tunable?
Yeah, I don't know. You could probably come up with some criterion like DIC or AIC or BIC or any of these information criteria, but I think you need to penalize more than the usual criteria, because you don't want a model that gives a really good fit. You want to leave what we found in the simulation study. So if we almost use the best fitting parametric model, then the performance over repeated simulations is no longer as good. We don't get high posterior coverage, and we don't get the smaller mean squared error. So you need to leave room for the non-parametric correction, but we thought, oh, the elbow is a reasonable criterion, but yeah, I think it's a bit empirical of what sort of the penalty term you use. So no, I haven't really got an answer. That's a good answer to that.
What about extended longitudinal data, in the sense that now we have a lot of functional data through wearables and stuff like that, and it's lots of individuals. How straightforward would it be?
Yeah,
Potentially can borrow strength across individuals.
Yeah, I'm not sure. I think it would be quite challenging. But I'm also not an expert on functional data analysis, so I think that would be another step up from this research.
You also have many patients, right?
Yeah, there's many patients. Yeah,
hundreds of patients.
Yes.
Instead of the 6 windmills you have in there.
Yeah.
And I think that is already a problem. For example, when you use some models like going beyond the standard regressive, say Arch and Garch, already doing that in a multivariate setting is not that easy, especially with the numbers for longitudinal data, where the number of patients are usually much lower.